So, in last class we have introduced a logic called temporal logic, by which we can capture or we can express the timing behavior. Now, we are going to see in details what is required in temporal logic and how we can express the properties in temporal logic. So, basically this is a specification language. We are going to specify the properties of our system, because in model checking I have said that we are having three components. One is your model of the system, second one is your specification, you have to provide the specification of the system, and third is your verification methodologies. Okay. So, basically we are going to look into the second component today, specification, how to provide specification, and for that we are going to use temporal logic. So, already I have mentioned that in temporal logic basically we are going to capture the timing behavior of the system. Secondly, if you look into the notion of timing, we are having two type of notion, one is your branching time and second one is linear time. Again I have mentioned about that we can capture timing in two different way, one is your discrete and second one is your continuous. Again I mentioned that how to specify the behavior, again we can look into two different ways, one is your qualitative and second one is your quantitative. In case of qualitative, we just specify that in future something is going to happen or not, or in quantitative we can specify that say after some unit of time something is going to happen in the system. So, in this lecture basically we are going to talk about qualitative issues of temporal logic. So, we have already introduced about the logics, we have talked about propositional logic or predicate logic or higher order logic, and now we are coming to the temporal logic. So, when you are going to look in the truth values of a temporal logic formula, basically the truth values of temporal logic formula is defined over a model, or always it is with respect to a model. We should have a model, and it is in this particular model we are going to define the meaning of those particular temporal logic formulas. So, temporal logic formulas is not statically true or false in a model. In some of the state it may be true, or in some of the state it may be false. So, it is not statically true or statically false like the other logic called propositional logic and predicate logic. So, it is a system dynamic behaviors, in some state it will be true or in some state it will be false. So, for that what requires we need a models. The models of temporal logic contain several states, and the formula can be true in some state and false in others. Now, what we can represent in temporal logics? So, we can express the statements like I am always happy. So, it says about the state of my mind, I am happy, I am always happy. On the other hand, it says that I will be eventually happy. That means, if sometimes I will be happy, or it says that I will be happy until I do something wrong. So, I will remain happy until I do something wrong. So, these are the way things that we can express. Now, we will see this is a simple example I am giving, but we will see what we can do. Now, temporal logics are having two kind of operators, one is your logical operator and second one is your temporal operator. Already we have talked about that logical operator, where we are having that disjunction, conjunction, negation, or say implication or XOR, like that all those logical operators that we have in other logics can be used here in temporal logic also. Along with that we are having another kind of operator which is known as temporal operator. So, this is the basic things that we are having. Now, we are going to see what are the temporal operators that we have in temporal logics. So, we know the meaning of other operators, logical operators, the meaning is similar with respect to the other logic like your propositional logic or in predicate logic. So, we will see what are the temporal operators that we have in temporal logic. So, basically here we are going to have four different type of operators. We said these are temporal operators, and these are basically related to or going to talk about the timing behavior of the system. So, one is your next operator. So, this next operator is basically represented by circle. Second one is your eventuality operator, it is represented by diamond. Third one is your globally or always, which is represented by box, and another operator we are having that until, which is represented by u. In this case, your next state, future and your global, these are your unary operator. It is going to take one particular formula, but until is a binary operator, it takes two formulas and it says talk about the meaning with respect to this formula. So, in your classical notation we use this particular symbol circle, diamond, box and until, but in textual notation this next operator is represented by x, eventuality operator or future operator is represented by f, globally or always operator is represented by g, and this until operator is represented by u. So, in case of x phi, if we write, that means in next state phi holds. If I say that f phi, it says that the formula phi holds eventually, that means in future, in some future state this particular formula phi will hold. So, g phi, which is globally phi, it says that phi is always true in the system, that means in all state phi is true. And phi until psi. So, it is a binary operator, we are having two formulas phi and psi. It says that phi remains true until psi holds, that means phi remains true until psi holds. In that particular case, we say that phi until psi holds in a particular state. So, basically we are going to look for this particular 4 temporal operators, and we will see now how we are going to represent them and how we are going to define the meaning of this operator. Now, already I have mentioned that temporal formulas or meaning of temporal formulas interpreted over a model which is infinite sequence of states. So, in a system we are having a number of states and basically we are having an infinite sequence of state. If we talk about reactive system, so you are going to define the meaning of those particular temporal formula over the states of a model. So, how formally what we can define? We can say that given a model M, so we are going to talk one model M and a temporal formula phi. So, we are going to talk one temporal formula phi. So, we will take these two components, one model M and one temporal formula phi. We define an inductive definition of the notion of phi holding at a position S j. So, in the system we are going to look for a position S j in M, and it is denoted by M S j models phi. It says that in a model M in a state S j, the formula phi holds, and we say that M S j models phi. So, this is the notion. So, the truth values of a temporal formula is basically defined in a model, and in a state we are going to say it holds or not, but they are having some other notion also. In the lecture I am going to elaborate those things. Now, in this particular case you just said that this is a state transition model. So, we can have different state called S0, S1, S2, S3, S4, S5, like that we can name the state of those particular model. And if you consider about some particular state, say Si. So, this is the model M, and we are basically concerned about this particular state Si. So, we will say that this model M in this particular state I, it models the temporal formula phi, if phi is a temporal formula. So, we are having a temporal formula and we want to check the truth values of this particular temporal formula. So, we have to check with respect to a model M, and we are going to define in a particular state Si. So, in this particular case we say that M Si models phi, it means in state Si in model phi holds. So, this is basically internal meaning of the truth values of our temporal formula. So, in this particular case I am saying that phi holds in this particular set, but it does not mean that phi holds in the entire system. It may be false in this particular S3 or it may be false in S4. So, that is why I already mentioned that the truth values of a temporal formula basically defines over a state in this particular model. In some state it will be true or in some state it will be false. Now, we are going to see the operator by operator, what is the meaning of these things. So, first we are going to look into the next operator. So, basically we have already mentioned that in textual notation next will be represented by x. So, this is the operator next I phi, that means the temporal formula x phi, it says that next phi. So, what is the internal meaning of how we are going to define the meaning of this particular formula? So, in a model M in state S j, it models x phi provided in the very next state x j plus 1 phi holds. So, if in a particular state phi holds, then what will happen? In the previous state, we are going to say that next phi holds. So, basically if I am going to look into this particular model, it is going from say state S0, S1, S2 like that, Sj, Sj plus 1 and further. So, what will happen if I label this particular Sj plus 1 with phi, it means that phi holds in this particular state Sj plus 1 of this particular model M. So, by meaning of these things, now we are going to say that where this particular formula next phi holds, then we will find that the state Sj models next phi, because when we come to this particular state Sj during the transition time, then we will find that from Sj wherever I am going in this next state phi holds. So, we say that x phi holds in this particular state Sj. So, this is the meaning of this particular next operator. So, x phi holds or x phi true in a particular state provided in next state phi holds. So, this is the meaning of your x phi, and we are going to define the meaning within a model. Now, next operator we are going to look for eventuality or future f phi. Now, how we are going to define? Now, you see the meaning of these things. We can say that in a model M in state Sj f phi holds. So, this is a temporal formula f phi. So, in future phi holds, basically it says that we are going to get some state k in the model where k is greater than j if we are going to look in a particular state j, and it says that model M and in state k that phi holds. Now, in this particular model, say this is my model, I am going to look for one particular state, say S j, say this is the state we are looking into it. In this line, we are going to get some state, say S k, and say S k is labeled with this particular phi. That means, it says that in S k phi holds. So, when we are going to say that f phi holds in a particular state, here phi is also another temporal formula. So, we are using a temporal operator phi. We are going to say in which state f phi holds. So, if in future we are going to get a state where phi holds, then we can say that in that particular state f phi holds. So, we can mark this particular state with f phi. So, what it says, if I am in state Sj, in this transition line I am going to get some state in future where phi holds. So, we can say that f phi holds in this particular Sj. So, that is why I am saying that there exists some k where k is greater than j in my timeline where M Sk models phi. So, if we are going to get such type of state in my model, then we can say that in my model in the state or the state that I am looking into it, I will say that f phi holds in that particular state. That means, in future we are going to get a state where phi holds. So, f phi holds in Sj. Now, next operator is your globally g phi. So, whether globally phi holds or not. So, again similar way we are going to define a model M, we are going to look at a particular state Sj, and we say that M Sj model g phi, provided we are going to get some k for all k, k is greater than equal to j, M Sk phi. That means, in all state where all state Sk where k is greater than j, if it models phi, then we will say that g phi or that Sj model g phi, globally phi holds. So, basically if I look into this particular state Sj, now we are having this particular state as your Sj plus 1 like that we are having. So, if all the states, if we have model it phi, it says that k greater than equal to j. So, phi must be true in this particular state also. Now, we are having an infinite sequence. So, basically we have to look for all the states that whatever coming in future. So, it is basically reason about an infinite system, but will come down in a state that everything can be represented by a finite state model. So, our number of state will be finite, but they will be repetitive in nature. So, we are going to get an infinite sequence. So, in that particular case, from a particular state Sj, if all other state in future that phi holds, then we can say that g phi holds in this particular state Sj. So, basically now I can label this particular state with g phi. So, we will say that g phi holds in Sj, because in all the states that can be reachable for that particular Sj, that phi holds. So, this is the meaning of globally operator. So, globally phi, it says that globally phi holds in a particular state if phi holds all the states in this particular system. So, this is the meaning of G phi, and the next operator is your until. We will say that already I have mentioned that until is a binary operator having two operand, one is your psi and second one is phi. So, it is psi until phi. Now, what we are going to say that again we are going to take a model M, we are going to take one particular state S j, we are going to see that whether in state S j of model M psi until phi holds or not. It will be holds if we are going to get some k, there exists some k, we are going to get a state k S k. So, in the model M or state S k, psi holds over there, and for all other k where this thing is your j is less than k, that M S psi model psi. Okay. So, in this particular case we are going to say that that particular state holds psi until phi. So, basically you can say that I am looking into a particular state say S k, it models this particular phi. So, in this particular case set phi holds in your state S k. Now, we are looking some other state say S j. Now, we have to see whether S j holds psi until phi holds in S j or not. It says that in future we are going to get some S k where phi holds, and in all the state in between them who are coming from this particular S j to that particular S k, psi must be true. So, they must be labeled by this particular psi. So, in that particular case we say that S j model psi until phi, that means psi remains true until phi becomes true. So, in S k phi is true, and all the states that is going from all the states that we are having in between from S j to S k for psi must be true. So, in that particular case we say that S j model psi until phi. So, this is the internal meaning of our until operator. So, in these things model M, we are going to mark this particular state S j by the formula psi until phi, provided it satisfied or fulfill this particular behavior that psi remains true until phi becomes true. So, these are the meaning of your until operator, and we are defining the meaning of this until operator in a model. So, basically now we have seen this particular 4 operator. One is your next state operator, second one is your eventuality operator, third one is your globally operator, and fourth one is your until operator. So, these are the 4 temporal operators that we have, and in classical notation we just represent x by your next state by your circle, then diamond is for eventuality, box is for globally, and u is for until. So, if you look into it, you are saying that if we are in a particular state, whether something is going to happen in future, either in next state or in all the states in the future. So, basically this particular 4 operator that I have introduced is basically forms the future logic. It is a future temporal logic. We are going to reason about the future behavior of the system. I am in a particular state, so the system is coming to a particular state. Now, from that particular state, how system is going to behave in future. So, if we are going to reason about this particular behavior, then we are going to look for this particular future temporal logic. So, this is future temporal. Since we are talking about the future temporal logic, whether we are having something called past temporal logic, yes, indeed we have. So, we will see that what is the notion of the past temporal logic. So, in case of your past temporal logic, like your future temporal logic, here also you are going to define 4 temporal operators, which are correspondence to those particular 4 future temporal logic. So, first one is your previous, we are going to talk about the previous state, and this is notationally we are going to represent it by say for future we are having this particular circle. So, in case of previous, that circle in between we are going to use that symbol tilde. It says that this is the previous operator, that means it is a past temporal logic, we are going to look for the previous state. So, eventually past. So, basically in future we are going to have this particular diamond. Okay. So, in the inside diamond we are going to write this particular tilde, then basically it is going to talk about this, or it is going to represent this eventuality in past, eventually in past operator. So, similarly we are having globally past or globally in past. So, again it is the same symbol we are going to use, that box is used for your globally operator. So, box inside this box we are going to put this tilde inside it, and we are going to say that this is the globally in past operator, and back to it is again corresponds to that until operator. So, back to is represented by this particular symbol. So, now we can reason about the past behavior of the system also. So, in that particular case what happens, we have to look for the past temporal logic. So, again like your future temporal logic, we are going to have this particular 4 operator, previous, eventually in past, globally in past, and back to. Now, you just see that like your future temporal logic. Now, we are going to look for the meaning of your past temporal logic. So, that previous operator, we are going to look for a particular model M, and we are going to look for state S j. Now, when we can say that state in S j of model M if the formula previous phi holds, provided we are going to get a state, this is a wrong symbol, it is not required. So, if M S j minus models phi, then we can say that previous is true in that particular state S j. So, when we are going to say that in this particular case, whether we are going to look for a particular state M S j plus 1, say this is your phi holds over here, then we can say that in this particular state S j your previous phi holds. Okay. So, this is the way that we are going to say that in if previous state that phi holds, then we can say that in that particular state phi your previous phi holds at that place. So, this is the meaning of a previous state. So, if we are in a particular state, whether if in previous state something happens, then we can say that previous phi holds in that particular state. Now, second one is your eventually in past. So, this is similar to your future. So, in case of future, you are saying that if we are in a particular state, in future something is going to happen or not. In case of eventually in past, from a particular state, we are going to say that whether something happened in the past or not. So, basically if I say look into this particular model M and say this is the state S j. Now, whether this particular state S j models some eventually in past phi holds or not, then in this timeline we are going to get look for some state and say that this particular state say phi holds in this particular state say S k, and where k is your less than your j, then we will say that eventually in past holds in this particular state S j. So, now we can say that this particular state models with eventuality phi. So, just say that meaning is corresponds to your future logic. So, if you are in a particular state, we are going to see in future something holds or not, but in case of past we are going to say that whether something happened in the past or not. So, this is the way that we are going to have the meaning. So, we are going to define the meaning of those particular past temporal logic operator with respect to the model also. So, similarly, next will be our globally in past, that means whether something happens globally or not. So, meaning is something similar to our globally operator in future, but here we are going to talk about similar ways. Say this is my model M. So, we are going to look for one particular state say S j, whether in this particular state S j say globally phi holds or not. So, in that particular case generally in past we are going to have something, but again we will restrict it to some other initial state, we will go up to that particular initial state only, because if you talk about past like in future we are having infinite sequence of states. So, that means it may happens infinitely in your past also, but always we can say that we are going to reason about from a particular state, that is the starting of my model, starting of my system. So, we will go up to that particular point. So, we are going to look for all k such that k is less than j, and say all those particular state S k this phi holds. That means, if I say that from S k all those particular states phi, I will just say that I am starting from this particular state, say that this is the I am going to look for this particular behavior only, then in all those particular states from S j if phi holds, then we can say that globally in past phi holds. So, we can say that we can mark this particular state with your this globally in past operator phi. So, this is the meaning of past operator. So, we are going for a particular state, and from that particular state we will see all the state in the past, and if that particular formula holds in all the past states, then we can say that globally in past phi holds in that particular state. Similarly, the last operator in this particular series is your back to phi. So, it says that back to phi, we will say that it holds in a particular state, phi holds in previous state, including present starting at the last position psi holds. That means, again since in past we may have an infinite state, but we will restrict to some initial states. Just say that we are going to look from this particular state, and we are going to look for a particular state, say S j. Now, we are going to say that whether in this particular S j back to phi holds or not. So, similarly, say in future something holds, or say until operator phi until psi. So, here phi back to psi, that means we are going to get some state in this particular model in past that psi holds, and all the states between S j and psi that phi holds. So, if we are going to get this particular model, say in some state psi holds in the past, and from that particular state to the state that of my concern, say S j, in all the state in between these two states, if phi holds including S j, because we are saying that j is greater than equal to k, then what we can say that in the state S j, this particular back to holds. That means, phi back to psi holds in this particular state. So, we can mark this particular state with phi back to psi. So, you just say that now we are trying to capture the behavior of timing system. So, when we are in a particular state, we are coming to a particular configuration. From that, either we can reason about the past behavior of the system, or we can reason about the future behavior of the system. In case of your past behavior of system, we are going to use the past temporal logic. So, we are having this particular 4 past temporal logic operator, previous, eventually in past, globally in past, and back to. If we are going to reason about the future behavior, then we are going to look for the future temporal operator, which is your next state, eventually, globally, and until operator. So, these are the 4 operator, basic operator we are going to discuss about it, and we have seen how we are going to define the meaning of those particular 4 operator, and we have seen that to define the meaning of those particular temporal operator, we are going to define with respect to a model. So, this model will come from our system. Now, just look for some example in this particular scenario. Now, we are saying that P implies F q. So, this is the formula. So, now I am giving a formula, say here P implies F q. Now, what does it mean? So, here q is a proposition. Basically, we have to see that P is a proposition, that means it is the atomic proposition, the truth values of your q may be either true or false. So, all atomic proposition will be treated as a temporal formula, because we have to see what are the temporal formula. So, all atomic proposition will be treated as a temporal formula. So, with temporal operator we can again construct a temporal operator. So, here in this particular case I can say that q is a temporal formula. Now, F q, that means whether in future q holds or not. So, in this particular case I will say that this F q is also a temporal operator. Similarly, P, again it is an atomic proposition. Okay. So, that means here I am going to work with 2 atomic proposition, one is q and second one is P. Since P is an atomic proposition, it can take truth value either true or false. So, that atomic proposition will be treated as another temporal formula. So, this is another temporal formula. So, in that particular case P implies F q, that means P implies F q. This is the implication operator that we have in your logic, and we say that this can be used in our temporal logic also. So, one temporal operator implies another temporal formula. So, these whole things will be treated as a temporal formula. That means, it may be something like that phi implies psi. So, here phi is a temporal formula, psi is a temporal formula. So, phi implies psi is a temporal formula. So, P implies F q will be a temporal formula where f is the temporal operator of futures. Now, we are going to say that p implies f q. If p is true in a state, then in futures state q is true. So, this is the meaning. Now, how to going to get the meaning of this particular formula? Always we are going to define it with respect to a model. Now, consider this particular model M. So, we are getting a state S k where q is true. So, this particular state S k q is true, and another state we are having say S j where p is true. Now, in this particular model, say we are going to have this particular state S 0, S j, S k, and to some model I can say that some S m and S n. Now, this formula p implies f q where it is true. So, if you look into it, again I will come into this particular notion. If you look into the future behavior, it says that if you look into, okay, I will go back to this particular definition again. Future, you just see that where I am having these particular things. So, here you just see that if a state S j, I am going to say that in state S j f phi holds, we are saying that there exists some k where k is greater than equal to j and m s k models phi. You just see this particular symbol there greater than equal to, that means it may happen that what will happen in case of when j equal to k, because it is, that means if psi holds in a particular state itself, according to the definition, what I can say that f phi holds in this particular state also, because this k equal to j. So, we will come to that particular point later on again. This notion is having some significance. So, that means again we see that by looking into this definition, we are saying that if phi holds in a particular state, we will say that f phi holds in that particular state. So, now come back to this example. So, since as per this particular definition, if phi holds in this particular state, then we can say that f phi holds in this particular state. Now, when I come to this particular state n, then from here in a future state phi holds. So, I can say that f phi, f q, here I am using this particular symbol q, f q holds in this particular state also. When I come to this particular state S m, from here also I am going to get a state in future where q holds. So, I can say that f q holds in this particular state also. When I come to this particular state S j, just say that from S j we are going to get a state in future when q holds. So, I can say that f q holds here also. When I come back to S 0, we will find that from S 0 in the timeline I will go down, and in future I am going to get a state S k where q holds. So, similarly I can say that f q holds in this state also. Now, we know the meaning of these things, know that logical operators say p implies q. Say if this is the implication operation, that means if p then q, if p is true then q must be true. But if p is false, you are silent. So, if p is false, then whatever may be the value of q, we are going to say that p implies q is true over there. So, here if you look into this particular model, so here f q holds. So, p is not true over here, but if p is false and q is true, then also you are going to say that p implies q is true. So, basically you can say that in S k your p implies f q is true. So, in the similar reasoning, I can say that in S n, S m and S 0 that p implies f q is true. Now, what about S j? P implies f q, again it will be true in this particular state, because now p is true. If p is true, then q is true, then we are going to say that p implies q is true in that particular state. So, basically in this particular state S j also p implies f q is true. That means, in this particular model we have seen that in all the states p implies f q is true. So, basically it state dependent, we have to look for each and every state, and when we are going to talk about a particular formula, so like that p implies f q. Now, we have to look for the truth values of each component. Now, here we are having components, say one temporal formula q, we are forming another temporal formula f q, then one temporal formula p. That means, we should know the truth values of this particular temporal formula in each and every state, then only we can talk about the truth values of this particular whole temporal formula. Okay. So, this is the way we are going to look into it. Now, another example you see that it is saying that P or X Q. Now, in this particular case, now again similarly we are having P and Q as our atomic proposition. So, like that what we can say now, P or X Q. So, P is a atomic proposition. So, P is a temporal formula, Q is a atomic proposition. So, Q is also a temporal formula, X is a temporal operator next step. So, X Q is a temporal formula. So, these two temporal formulas is connected by this OR operator. So, this is also a temporal formula. Now, we are going to look for the truth values of this particular temporal formula. Now, in this particular case either P is true or X Q is true. Now, in this model if I am having this thing. So, the similar way I can say that P is true over here and Q is true over here. So, in this particular state what I can say that X Q is true over here. What about this particular state? Because X Q is not true, because Q is not true in the next step. So, X Q is not true. So, here Q is true. So, in this particular state I can say that X Q is also true over here. Now, since this is your P or X Q, now we will see that in all the states either P is true or X Q is true. Okay. So, here I am going to say that P or X Q is true in all the states. Now, if I simply sense this operator from P and X Q, then what will happen? We are not having any state where both are true. So, in this particular case I say that this P and X Q is false in all the states. Now, I will slightly modify these things labeling of this particular state machine or in all the states. I said that in S0 also P holds. Okay. Now, in this particular case you say that in S0 you will find that both P is true and next Q is also true. That means, you can say that if this is my model M. So, in this model M in state S0 that P and X Q hold. So, you just see that in this example what we are getting only one state S0 where P and X Q is true, but in all other state P and X Q is false. But if we talk about P or X Q, we will find that in all the states P or S Q is true. So, this is the way now we have to look for the truth values of each and every temporal formula in each and every stage, and then only we can talk about the truth values of a particular temporal formula in a state. So, it is state dependent. In some state it will be true or some state it will be false. Now, come to this particular state, again we are having now here we are using P until P or Q until R. That means, we are having P, Q, R as your atomic proposition. Okay. We are starting with 3 atomic proposition and we are saying that P or Q until R. So, Q and R are temporal formula. So, Q until R is a temporal formula, P is a temporal formula. So, P or Q until R is a temporal formula. So, now what we are saying that either P holds in a state or Q until R holds. Now, if you look into this particular model M, then we will find that in state R Sk this R is true, and when we come back to this particular set, say I will just label it as say Sm and Sn. So, in this particular Sn we will find that Q until R is true. When we come to that Sm, we will find that Q until R is true. If we come back to this particular state Sj, you will find that Q until R is true. When you come to S0, you will not find that Q until R is true over here, because Q is not true in that particular point. Now, when we are going to look for P or Q until R, you will find that in this 3 state Sj, Sm and Sn, Q until R is true. So, P or Q until R will be true in this particular 3 state. When you come to this particular S0, since P is true, we will find that P or Q until R is true. When you come to this particular Sk, then we will find that neither P is true nor Q until R is true over here. So, we will find that P or Q until R is false in this particular state Sk. So, this is the way that we are going to look for the truth values. So, we are just looking into some examples to get the meaning of those particular temporal operator. So, now I think you can look into it when I can talk about P and Q until R. So, this is similar. In earlier case we are having P or Q until R, now we are talking about P and Q until R. So, P and Q until R. So, similarly, you can inspect this particular thing Q until R. So, here we are going to find out, now say that I am just going to look into it. If we look into that P and R is true over here. So, what is the status of your Q until R? Q until R is false over here. I am going to talk about Q until R. So, if you look here that Q until R is false over here. If you look into this particular state, Q is true until R is true. So, you can say that Q until R is true over here. When I come to this particular point, again you will find that Q is true until R is true. So, I will say that Q until R is true over here. When you come back to this particular state, again you will find that Q is true until R is true. So, Q until R is true over here also. So, again as such I am going to give the name S M and S N to this particular two state. Now, we have to say that P and Q until R. So, in that particular case both P and Q until R must be true in a state. So, here we are going to get that in S0 both are true, in Sj both are true. When we are coming to this particular case in your Sn, both P and Q until R is true. So, you will find that in this three state P and Q until R is true, but when we are coming to state Sn and your Sk, you will find that P is true in both the cases, but Q until R is not true in these two particular states. So, we will say that Sn and Sk. So, this formula is not true, basically it is false. Okay. But in these three states I can say that it models this particular formula P and Q until R. So, in the model M, if I am going to take this particular state of state, I will find that in this three state P and Q until R is true. Now, this is another formula that I am talking. So, we are going to have this circle and inside that I am having the tilde, that means this is the previous operator. So, previous operator means this is an example of our past temporal logic. So, in that particular case you said that P and previous Q. So, you have to see whether P is true and the previous state Q is true. So, if you look into this particular, this is a simple model that we are having. So, you say that here if I am in this particular state say Sk, you will find that in the previous state Q is true. So, I can say that previous Q is true in this particular state. When I am in this particular state, say again I am marking it as you say Sm and Sn. So, when I am in your Sn, you will find that in previous state your Q is true. So, I will say that previous Q is true in this particular state. Similarly, when we come down to this particular state in Sm, again you will find that previous Q is true. Similarly, in Sj, I will find previous Q is true. So, we are talking about P and previous Q is true. So, we are going to get that, and you just say that since this is the starting, I am saying that in past we cannot go beyond certain points. So, we will say that we are having some start state and we are going to starting from S0. So, here that previous Q is not true, because thus we are saying that we know the behavior from this particular point. We do not know the behavior of the system prior to this particular state. So, here we cannot talk about that whether previous Q is true or not. So, here I am not going to say that P and previous Q is true, but in this particular fourth state Sj, Sm, Sn and your Sk, that P and previous Q is true. Okay. So, this is the way we are going to look for the truth values of our temporal formula. Now, I will give you some question. Let us see whether what we are going to do. Here says that what does the temporal formula P implies the tilde inside box Q mean? Give an example where this formula is valid all the states. Now, say I am here in this question, what I am giving? I am giving a temporal formula P and I am writing a symbol this is basically diamond, and inside the diamond I am having the tilde and q. So, what this particular symbol means? I think you can very well identify. This symbol means basically eventually in past. Okay. So, diamond is future. If I write tilde in diamond, then we say that this is eventually in past. So, we are going to say that you are going to look for this particular thing eventually in past q holds or not. If p implies eventually q. So, it says what does this temporal formula p implies eventually in past q means. So, that means we are going to say that if p is true, whether eventually in future past q was true or not. So, give an example where this formula is valid in all the states. Now, if we talk about such type of question, give an example, that means we have to come up with a model, and we have to see that in this model we have to look for the truth values of this particular formula in this model, and we have to see whether this formula is true or not. Now, we have to come up with an example where this particular formula is true in all the states. So, now this is basically what it says, that p implies tilde inside diamond q means if p holds in a state, then eventually in past q holds. So, if q holds in a state, that eventually in past q holds. So, it is a very simple model that I have come up with these things. So, we are talking a state S k, and beyond that in future we are going to have said, we just think that this S k is the current state. I am going to look into it, that S 0 is the starting point of my system, and just say as I all these things I am going to give the name of these two things S m and S n. And what was my formula? It says that p implies eventually in past q means. So, basically I are going to look for a formula p implies eventually in past q holds. Now, we have to look for this particular formula first. Say, since q is at atomic proposition. So, eventually in past is also temporal operator, p is a atomic proposition. So, it is a temporal formula. So, even we are looking for a temporal formula. So, eventually in past q holds. So, if you look into S k, if you go in the past direction, then you will find that we are getting a state S j where q holds. So, I can say that eventually in past q hold in this particular state. So, similarly in S m and S n also eventually in past q holds. Okay. Now, in S j I cannot say these things because we do not know, because q was not true in S 0, and again S 0 we cannot reason about this thing because we are just saying that this is the starting point. Beyond that what was happened we did not know about this thing. So, this is the formula we say now p implies eventually in past q holds. So, if p holds in a state, then eventually in past in q must hold. So, if you look into the S k, this formula is holds over here. Okay. So, this is the state. So, similarly, but if p is false, we do not have any meaning over there. So, we not required to look for the truth values, because if false implies, because we know that implication if p is false, that formula is true in this particular state. So, in your S j, S m and S n, this formula holds. So, in all those particular state, p implies eventually in past q holds. Now, look for another one. I am saying that express the following information in temporal logic. So, basically we are going to reason about it. We are having some behavior. Now, whether we can express these things with temporal logic or not. We are saying that express the following information in temporal logic. P is true in next state or the next but one. Here you just think that P is a atomic proposition. So, we are talking about one atomic proposition P, or since atomic proposition or temporal formula. So, it can be replaced by any temporal formula phi also. That means, P is true in next state or in next but one. So, now whether can it be expressed in temporal logic? Let us see. We can say write the formula for this particular statement x p. We are going to say that in next state p holds and x x p. So, you see that next to next state p holds. So, what I said that p is a atomic proposition. So, it is a temporal formula x p next state p holds. So, we said that this is also another temporal formula. Again I am writing this particular next operator x of x p. So, again these things is also temporal formula. We are saying that p is true in next state or next but one. So, we said that xp is basically next but 1 and xp is your next state. So, now in this particular case, now what will happen? Now, we are going to look into it. Now, you can say what is the truth values of these things, then again you have to look for one model. Say if I am going to have some model like that. So, this is a model, say in this particular state, say p holds and in p holds. Then what will happen? If you come to this particular state, you will find that xp holds over here. In this state also xp holds over here. If I come to this, say I can say that this is your Sm, Sn and say Sk. If I come back to Sn, then what will happen? You will say the next state p holds and next state and next state also p holds. So, here x p also holds in this particular state. So, I am having this OR combination. So, you can say that xp or xxp hold in this particular state. Similarly, since I am having this xp or xxp, so in Sn also this particular formula holds. So, what happens? I can say that in Sm and Sn this particular formula xp or xxp holds. Now, if I replace this formula by say xp and xxp, that means in next state p holds or and next state p holds. Now, since I am having this particular conjunct and operation, then you will find that this particular formula holds only in the state Sm. It is not true in Sn, because in Sn xp holds, but xp not holds. So, that is why I am getting only Sm, where this xp and xxp holds. Now, another question you just see that you can think about it. P is an atomic proposition. Now, I am saying that write a temporal formula for P is infinitely often true. I am talking about P is infinitely often true. That what does it mean? So, it is infinitely often it is coming, that means it is true and after sometimes again it will be true. So, in temporal logic you can write this behavior in this particular case, say globally Fp. So, infinitely often, that means globally it should come, what globally it should come? In future P holds. So, we are saying that P is infinitely often true. It is not like that if Gp, if I say that globally P is true, it is different and infinitely often it is true. That means, it is not always true, but infinitely often it is true. It is coming true after some instance of time. So, that is why we are saying that globally Fp holds. So, it is infinitely often it is true. Now, can you give a model for this particular statement where it is true in all the states, because globally infinitely often it is true. So, it is you can construct it, because if you know the behavior, say I am just going to give one example, say I am having a state machine something like that, and say that in this particular state say P is true. Now, say these are the states, say S0, S1, S2, S3, S4. Say I am coming up a very small models. So, globally infinitely often this, that means P must to infinitely. What happens? I can make a state like that. Now, these things is this execution trace S1, S2, S3, S4 is repeating. So, in this particular case you say that wherever you are in future, that we are going to get a state where P is true. That means, P is not globally true, but infinitely often it is true. So, that is why we are saying that globally Fp is true. When we say that P is infinitely often it is true. So, this is now in this class what we have seen. We have seen what are the temporal operators that we are having. We are having two type of logic. One is your past temporal logic and another one is your future temporal logic. In both the cases we have seen 4 operators, the basic operators. One is your next, eventually, globally and until. And we have seen how to define the meaning of those particular temporal operator. We are going to define the meaning with respect to a model. So, we have seen what is the meaning of those particular operators and give you some clear idea about those particular temporal operator. I have given some example and along with that we have discussed some question also. So, with this today I am going to wind up. So, in next class we are going to look for a particular temporal logic. Now, we are having with this particular 4 temporal logic operator, we are having several kind of temporal logics. So, we are going to look for a particular class and we will discuss about that particular class, and in our lecture we are going to use that particular class. Okay.